Hello everybody, welcome back to the channel. It's W3 here. So in this video it's part 2 of the Linux Kernel Module Rootkit. Now for those that haven't seen part 1, there's going to be a link that'll come on screen now, and I suggest you watch part 1 first so that you can follow along with part 2. It will also be in the description and probably a pinned comment as well. Now for those that have watched part 1 and are now on part 2, I'll just quickly recap what we did in part 1. So in part 1 we created a basic Linux kernel module like code template. We learnt about the callsims lookup name function and the syscall table. We also learnt about the license, so including a module license so you don't get those errors, and also about the kernel libraries and not to use user space libraries, and so on and so forth. So now we are here basically. This is the code from last time. This is where we got up to. So before we get going, I'm going to actually just move this to the side because it is a Linux kernel. It's a what's it called? It's a preprocessor directive. You don't have to, but I've just seen a lot of people that put the preprocessor directives to the side like that, so I think I'll do that as well. And also I forgot to end it with a hashtag end if. Now it worked last time because we were just returning, but if there was to be more code you'd need to end if because it's preprocessor, which means that when it compiles, if this version is greater than that, it will compile this and it won't compile the rest of the code that would be in another preprocessor directive for a different version. So basically, yeah, we could have used just a normal if else, but what's the point when we can actually just compile and use less code in the final executable basically. So preprocessor directives are actually quite useful, and it's something in C basically. Yeah, it's good. So we've got the syscall table function and we are hooking to the syscall table. Cool. So what we need to do now is we need to actually have a function that can protect and unprotect the memory, because the memory is actually protected, so we can't actually overwrite the syscall table as it stands, and we need to unprotect the memory. Now Intel processors, they have a register called CR0, and that is set to basically protect the memory. And we're gonna change a bit. We're gonna change the 16th bit in the CR0 register, the control register 0. We're gonna change the 16th bit. We're gonna flip it so that the memory becomes unprotected. So if we were to Google Linux kernel CR0 memory, Linux kernel rootkit will go. And this should bring up some good it will bring up basically some information, you know. But there's a good post I saw. This was it. Yeah, when I was researching about rootkits and that, obviously it says here we can no longer easily disable CR0 WP, which is write protection. And they've got it here. This commit makes write underscore CR0, and then we're reading CR0. And then we're ORing it with 0x10000. So basically, when you read the control register 0, and then you OR it with this here, which is basically the 16th bit, is a 1. It will flip the 16th bit in the read control 0 data. And it says it's useless here. Next time you see a 5 something Linux kernel, good luck. And then according to this Stack Overflow question, we cannot disable CR0's write protection bits, set R0 page to read write. So before, people were using the write_cr0, which is a function in Linux that is used probably for flipping the bit properly and so on. They were using that, but they've obviously put some sort of defense in. But obviously this person, he found this method online, and it's actually quite simple. Instead of using their method of write_cr0, you literally just change the name of the function, and then you paste in the actual function itself anyway. So you basically create your own write_cr0, and then there's no stopping you from using that function because it's yours anyway. So that's quite a simple, get around really. Just create your own version of the function and use it. And that's basically what they're doing here. So all you have to do is just copy this function. It's a little bit of assembly, volatile. You can Google and read into it a little bit more, but I just copied it and pasted it. I also did read a bit later on, but I won't go into it in this video. And then obviously we just got protect_memory. So we write the cr0, and then to unprotect it, we write cr0 and we OR it. We're ANDing it with an inverse of the 16 bits. So basically what that's doing is we're flipping the 16th bit basically by ORing it, and then this here is an inverse. So 0x00010000 is actually 11101111, etc. We AND it together. So if we just copy this in here like that, so now we've got the function that we are going to use to be able to write to the CR0 register. So we're going to be able to write to it to flip the 16th bit to protect memory, and then we can flip it again to unprotect memory, and so on and so forth. We've written our own function which is exactly the same as write_cr0 basically, but we've just obviously made it our own, so it doesn't go through any of the checks that function does if we were to use the original function from the Linux kernel basically. So it's very simple and it works great. So what we need to do now is we need to just create two functions, one for unprotecting it and one for protecting the memory. So let's do that. Okay, so I'm going to copy and paste these two in here as well. I'm not going to type it out because it's going to save a bit of time and I can actually explain it instead of just typing it for you. So here we've got disable write protection. So we've just got a static void unprotect_memory, takes in void arguments, returns void, so nothing, and it's static so that this function only belongs to this file here. No other files can call it. So as you can see, we're calling our function write_cr0_forced, and then the arguments that it takes is read_cr0. So that function returns basically the value of the cr0 register, and by using this ampersand, which is a bitwise operator, we are ANDing the bits of the value. So the value that is returned from read_cr0, we're ANDing those bits with this value here. So this value here has got the unarray operator. Let me zoom in a bit more. Okay, it's got the unarray operator, so that's going to reverse whatever this is. So as we can see, it says here reverses the bits, so 0x10000 becomes 0x01111. So it becomes that first, and then we AND the bits together. Now, why is it 0x10000? Because we want to flip the 16th bit. The 16th bit in the CR0 register is the write protection bit. But you might be thinking, but why aren't we doing the 4th bit? Well, each one of these numbers is 4 bits. It's a nibble. And you might be thinking, why aren't we doing 1 to 4? So that's 4, 8, 12, 16. Why are we going and doing another one? Well, bits, they start actually, this is 4 bits total. This first 0 is 4 bits, but it's from 0. It starts from 0, so 0, 1, 2, 3. And then the next one, then the next one, and so on. And you can actually see this quite easy as well. If you make a int and then say a, and then do 0x, and then 1, 2, 3, 4, 5, and you put your cursor over it, it says it's an int, and then we've got 65536, which is the value if you were to do the 16th bit, basically 16th 16 to the power of 2, base 2. So that's why we have that value. So yeah, this becomes 0x0111. So obviously the read underscore cr0 0, the 16th bit is a 1, so it's protecting the memory, the write protection. So we're ANDing the 16th bit with a 0, so 0 and 1 becomes 0. We've turned it off, we've unprotected the memory. When we want to protect the memory, we read the CR0 register again, and now obviously the 16th bit will be a 0 because we would have turned it off before. So we're gonna OR that with this value, and this value is 0x for hex, and then we've got 1 0 0 0 0. So in this value, the 16th bit is a 1, and we're ORing that with a 0. 1 ORed with 0, or 0 ORed with 1 becomes a 1. We've just flipped that bit back to a 1. Now the memory is protected, and that's the way that I've done it in this. Obviously, if we look at the article, they have protected the memory just by doing CR0, and when they unprotect it, they're doing the AND with the unirate operator. Now they're doing that because obviously this CR0 is probably a variable that is equal to what the read underscore CR0 value was as before. So they've saved the value of the read CR0 register before they started flipping bits. But we're not saving any register data. We're just going to read the CR0 register and just flip the bits, because we know that obviously it's starting with a 1. When we want to unprotect it, we'll flip it to a 0, and then when we read it again, it's obviously going to be a 0 from before, and then we can just flip it to the 1 to turn it back on. Nice and easy. We've also got our print K for printing to the kernel underscore info, and then we're just saying unprotect memory, protected memory, just so we know that we can, it's working basically. So these are the 3 functions that we need for basically protecting and unprotected memory for when we want to hook and write to the syscall table and so on. So now that we've got these out of the way, we can actually move on to hooking a syscall using the syscall defines, using the syscall table names that correlate to numbers in the uni.std.h header that we looked at before in part 1. So let's move on to that now. Also, just another quick one on the CR0 control register. If we Google CR0 register write protection, you'll get some data, Wikipedia and so on. I don't think it is just an Intel thing. I think it's like 32-bit, 64-bit registers or something like that. But anyways, we've got here what's the purpose of x86 CR0 WP bit, and it says here, quoting from Intel 64 and IA-32 architecture software, developers manual volume 3 APG something something. We got WP write protection bit 16 of CR0 when set inhibits supervisor level procedures from writing into read-only pages. When clear, allows supervisor level procedures to write into read-only pages. So the syscall table is part of read-only pages, and that's why we are gonna we're flipping the write protection bit, and then we are writing to the syscall table our new hacked syscalls, and then we're protecting the memory again. So that's just a quick note on the CR0 register. And we also need to include a library, so we can use the read_CR0, the read control register. So we're going to include asm/paravert.h. Okay, so now what we need to do is we need to create some function pointers to point to the syscall table, so we can store the original syscalls and then we can start hooking the syscalls. So before we begin, let's just go through and see what we have so far. So we've got a syscall table variable. It's a pointer, unsigned long pointer. What we're going to do is we're going to delete this and we're just going to make it equal to nothing. We're just creating the pointer at the minute. We've got our write_CR0_forced, which is basically the same function that they have in the kernel, except it doesn't go through any of their checks or their traps or whatnot. So we can use that, and then we unprotect and protect the memory by flipping the 16th bit in the CR0, the control register 0 register. So that's cool. We've also got our get_syscall_table, which returns a unsigned long pointer. Now this is useful so that if you're using a different version, you can create another preprocessor directive for different versions, so that you can get the syscall table using different methods. We're only going to use this method for now because obviously this works for 4.4.0 and above, or over 4.4.0, so that's fine. But we're going to add a little bit to it. So we've got unsigned long pointer syscall_table. That's a pointer, and then if this version, we get the syscall table by doing this. And what we're going to do is we're going to do a else preprocessor directive. So if that, do that, else, and then we're going to do syscall_table equals, and then we're just going to do null. So it returns obviously a void pointer 0. So 0 is typecast to a void pointer. That's what that equals. So it's going to return a void pointer unless we are using the version for this preprocessor directive and we get the syscall table. That will be useful later, as you'll see. So we've got an init function which initializes the LKM, which is cool. We've got our exit, which obviously exits the LKM. So we've got our __syscall table thing here, which is equal to our function. So obviously we're going to get the syscall table, but if it doesn't, it will get null. And what we can do is we can say if __sys_call_table is equal to, we can say equal to null, or we can just do like that. So if not syscall table, then we can just like return 1. So that means there was an error basically. And we can print kern_info and then syscall, and we can do __sys_call_table is equal to null. Actually, let's say return error, so error stands for error, and we're going to create a int err equals 1. So what we'll do is we'll just, if not syscall table, we'll print syscall table is equal to null, and we'll say error, that's equal to null, and then we'll just return that. So that way we don't start hooking syscalls and trying to save the original syscall tables and so on and so forth. We're just returning, and we're not doing any more because obviously it's null, so we're screwed. So yeah, that's cool. And we'll leave exit like that for now, but we'll also introduce a int err equals 1, so error equals 1. And yeah, nice. So let's go up to the top again. So now we need to create another if preprocessor directive. so that we can decide which argument type we're going to use, because the syscalls, there's two types basically. And I'm going to create we're going to do if def, and then we're going to do config underscore x86 underscore 64. Now that's basically saying that if we're on a machine that's x86 64, it's going to do the code below until it hits a end if preprocessor directive. So now I'm going to just paste in this little comment that I wrote, as it explains some stuff that you need to know. So as we can see, it says at least on 64-bit x86, it will be a hard requirement from version 4.17 onwards to not call system call functions in the kernel. It uses a different calling convention for system calls where struct pt_reges is decoded on the fly in a syscall wrapper, which then hands processing over to the actual syscall function. So yeah, syscalls from version 4.17 onwards, they have a struct which is pt_reges, a struct as their parameters, as their arguments, and you pull the arguments of the syscall from the struct. But originally you didn't have to do that, and you just had the arguments in the syscall, as we'll see. And we're going to do both as well. So first of all, we can do another preprocessor directive, and we can do if, and then we can do Linux underscore version underscore code is greater than or equal to, and then kernel underscore version, and then we're going to do 4.17.0. So then if it is greater than or equal to kernel version 4.17.0, we're going to do a define. So we're going to define, and then we're going to do pt_reges underscore syscall underscore stub as 1, because it's using the pt_reges syscall stub basically. Now once we've defined that, we are now going to create a type def. So we're going to create a function pointer type def. This will be handy, as you'll see in a minute. So we're going to do type def ASM linkage, because obviously the syscalls, they start with ASM linkage if you look at them on the in the kernel, and then it's long, and then we're going to do brackets pointer pt reges and then underscore t. When you're making a type def, it's quite common to do the name, say, and then underscore t. That's quite a common thing. Now it's in brackets because if we didn't have it in brackets, this would be basically a function that's returning long pointer, but putting it in brackets makes it a function pointer, and obviously it's a type def as well. Now the arguments is going to be const struct pt_reges and then pointer reges. So as you can see, we only need to make one type def, which is pt_reges underscore t, because all syscalls from 4.17.0 and above, they use this struct here, and then we pull the arguments for each syscall out of that struct. So we only need one type def, so that's quite handy. So we're going to create a kill. We're going to create the original kill function pointer. So we're going to do static pt_reges underscore t for type, then orig underscore kill. So there we have it. We've got a function pointer as orig underscore kill. Nice and easy. And if we wanted to add other syscalls, we just do static pt_reges underscore t orig and then the name of the syscall. So now that we've got that, we can do else. So if the Linux version is not equal to or above this, we won't do any of that, and we're going to do what we do below now. So we're going to create a type def again, ASM linkage long, except this time we need to create a type def, a function pointer for each individual syscall, because as you'll see, they use the older version basically, and we're going to do pointer orig underscore kill underscore t. So we're still making a function pointer type def, because it's going to be useful in a minute, as you'll see. But the arguments is going to be PID underscore t, PID, and then int sig. These are just the same arguments as if you were to look up the syscall in the kernel, GitHub code, etc. So yeah. And now what we can do is we can do orig underscore kill underscore t, and then orig underscore kill, like that. And if you see, we've actually got the same name. So this is original orig underscore kill, and so is this. That's useful because when we create our function to store the original syscalls, we don't have to do any if or else or different names. It doesn't matter if the version is doing this bit here or if it's doing the else. The name is the same, and we're gonna store the syscalls just the same. We also make this static as well. So that's good. Now what we have to do is we have to just end if. So we're ending this here, this preprocessor directive, end if, and we're going to make another end if for this here as well. So that's good, nice. So now let's create our store function to store the original syscalls. So what we're going to do now is we're going to create static. So we're going to do this here. We're going to do static and then int, because we want to return an integer to make sure everything was fine. 0 if it's good, 1 if there's an error. Store is the name of the function, and then we're just going to put void because we're not using any arguments, and we'll create our empty function like that. So we're on our store function. So I'm going to paste in this comment here, and as you can see it reads, if Linux underscore version underscore code is greater than or equal to kernel version 4.17.0, syscall use pt underscore reges underscore stub, basically. So we've got to use pt reges. So we're going to do a if preprocessor directive again. So if, and then we'll do pt reges underscore syscall underscore stub. And then we can do a comment, and then we're going to do kill. So we know this is for kill. And then we're just going to do orig underscore kill equals, then we're going to typecast to pt. Let's first of all do underscore sys. So we're going to use the syscall table, and then we're just going to use underscore nr underscore kill. So we're going to the syscall table, and then just like an array, we are literally indexing to where the kill syscall is. Now this underscore nr underscore kill, the nr stands for like number reference, and then obviously kill. We saw this in the uni std header file in the Linux GitHub on part 1. And you see that this name here is literally just a define, so it's defined as a number, so it's just some number basically. And this gives us the place in memory where the kill syscall is, and then it's going to return the kill syscall address. But we cannot leave it like this because the orig underscore syscall is of type pt reges. So what we need to do is we need to typecast it, so pt reges underscore t, just like that, because original underscore kill, if pt reges underscore syscall underscore stub is defined, if it's a 1, then orig underscore kill, as we can see here, orig underscore kill is of type pt reges underscore t. So we just type def in it, that's all, no big deal. And then obviously we can do else. So preprocessor directive for else, and then I'm going to copy this comment in here. So if the Linux version is lower than the kernel version 4.17.0, then we do else. And then all we're going to do is exactly the same. Comment for kill, and then we're just going to do orig_kill equals, and then the type is orig_kill_t. So we're typecasting it to now this type, because obviously it's not that. It's going to be using orig_kill, which is of type orig_kill_t, which is taken in obviously, which is this. Basically, it's different type. And then we're just going to do the same sys_call_table, which is pointing to the syscall table, if you remember. And now we're going to index it. So it's like putting a number in, except we don't know the number, but we do know the name. And we do know the number if we look at the uni std header file and so on. But like I said, we use a name because the number can change, but the name will always remain the same. So that's good. And then what we can do is we can just do end if. So we've ended this preprocessor directive if else statement. And then we can do return 0. So as you can see as well, it doesn't matter which version that we're on, it's still orig_kill. And that's because we use typedefs to get it like that. If we didn't use typedefs and we just created a function pointer like that, we would have had to write something like this, orig_kill_t, and then to like use it we would have had to dereference it or something weird, like, yeah. So that's cool. And what else can we add to it? We can add a print statement so that we know obviously that it's worked basically. So we can add this here like this, original_kill table entry successfully stored, and we'll write the same for this one here like that. Nice and easy. So we've got our store, and we can store the original syscalls. Doesn't matter which version, it uses the same name, so that's nice. So we've returned 0, that's good. So we've stored our kill syscall. Now we want to hook that syscall. So what we're going to do is we're going to also create a hook function. So we're going to do static int hook, and then void, taking void, no arguments, and then we'll give it a space. Let's create a little bit more space so you can see it maybe a bit better. So in this function, in the hook function, all we need to do is we need to hook to our hacked syscall basically. So for now I'm just going to return 0 because we haven't actually made that function yet. So let's make that function, and we'll make that up here. So we're going to make both versions of the function for kill. We're going to make the PT regs and the one before PT regs, the original, what it used to be like. So we're going to do static ASM linkage long, because if we look at the if you were to look at the kill syscall in the Linux kernel, it would be ASM linkage long, so on and so forth. And we're just going to do hack_kill because it's the hacked one. And then for the arguments, we're just going to do const struct pt_regs and then pointer regs, and then that. So we can also make another preprocessor directive. We can do #if, and then this is where the pt regs_syscall_stub comes in handy. If pt regs_syscall_stub. So if this is defined, it means that we're using these pt regs syscall stubs, and then we can do else we're using the normal version. So I'll leave this blank for now, but as you can see, we're taking in construct pt regs pointer regs. Otherwise we're doing static ASM linkage long, hack_kill, so the same name, which will help us later on as well. And then for the arguments, we obviously need PID_T, PID, and then int sig, and then like that. And then we're going to do #endIf to end that preprocessor directive. So let's move that out of the way. So we just focus on this here. So to get the arguments out of this struct, we can use a simple thing. So basically, if we go to Google and we do Linux syscall reference, you can see what comes up: syscalls 32, Linux syscall reference, syscall 64. So I'm going to click on this one, 64 Linux syscall reference, and as we can see, we've got all the syscalls, then we've got the registers that they go in, and then the actual argument that it relates to. So for the PT regis, this is what we can use, and basically it tells us what register is holding what argument, basically. So we can just go to kill, we've got sys_kill, so PID_T, and then PID is the RDI, so DI, and then int sig is in the SI register. So obviously the old version has the arguments here, but in the new version we have to pull it out of the struct. So we know that int sig is out of the SI, so what we can do is we can do int sig equals regis, because obviously this is a pointer to the struct, and to use the pointer that's at the struct, you use it like that, and then we can just do SI. So we're pulling the int sig out of the SI register, and that's the only one we need for the hacked_kill. We just need the SI is the signal. Yeah, we just need the signal number, because we're not actually doing anything with the PID. We're not going to call the original syscall. We just want to know what number is being used. We're going to then do our own thing, and yeah. So we got sig regis SI. We can do if sig is equal to sig super. Now we haven't created sig super yet, so let's go up here and let's create a little what's it called? Let's create a little like an enum. It's called enum signals, and we're just going to do sig super equals 64. No, it's a list. Sig super equals 64, and then sig in vis say equals 63, and we could just put a comment like become root hide become invisible. You could make these any name you want, and if you run that signal it could do any function you want. But let's just call it that for now, and then obviously that as well. So we've got if the sig is equal to sig super, we'll just print yeah. So we'll do print k, and then kern_info, we'll do signal, and then %d is equal to sig super, and then %d, and then hide itself /malware /etc, and then we'll just do sig and sig super like that. So obviously I'm not gonna make a function to hide itself and stuff like that. I'm just hooking the syscalls and storing the original ones, etc. You could do all this yourself, but this is just a base. This is a good way of yeah. So we've got return 0, so we just return 0. So as you'll see, we're not actually going to call the original syscall like you do on, say, hacked git dents, the git directory entries. You would look at the directory entries until you see your magic file prefix, and then what you would do is you would store all the directory entries in a array or something, but then you would remove yours, and then you would forward that data onto the original syscall so that your original file is not in there, and then the original syscall will do its thing with obviously improper data because you've took yours out. But for kill, we just need to see if it's the same signal as what we've said we want, and then we'll just do something with it, and then we'll just return. We're not going to call the original one, but if it's not the signal number that we're looking out for, which is obviously sig super, which is 64, and sig invis, which is 63, what we can do is we can just return and then orig underscore kill and then regis. So if it's not the signal we want to look out for and we want to do something with, then it just returns what the original syscall with obviously the regis, which is the arguments that it should have, and it will just run the original syscall, which, you know, does whatever it does basically. And then we can do also else if, and then else if sig is equal to sig invis, then we'll do the same, except we're going to change sig super to sig invis. And sig super, yeah, actually that was meant to become root, this one. Become root, this one hides itself. And we'll change this to sig invis. So yeah, if the signal number integer is not equal to sig super or sig invis, then it's just going to run whatever the signal would be on the original syscall. So it doesn't matter which process ID number you give it, because it's not going to actually do anything on that process ID. It's just going to run whatever function that you have in your hacked syscall, which we don't have a function, but you could add it, and then it's just going to return anyway, so that's fine. So we've got this one. So now for the other hacked kill function, which uses obviously the original sort of way of doing things, has the arguments in here, it doesn't use a struct, then we can just do we could just literally copy this here like that, because obviously we've got sig here, the PID we don't need to use, and then we can copy this here as well like that. And I'm also going to add in this here. So we've got a hacked call syscall. So anytime that the kill syscall is used, it will print, because obviously other programs and many other things will be using syscalls all the time, and it's going to go through your hacked syscall, you know. So yeah, we can see how many times it's being used and when it's being used, and we'll also add it up here as well. So yeah, now we've got two syscalls, and it's for the hacked syscall, hack kill. One's for the PT regis syscall stub, the other one is for the non-PT regis syscall stub. So now what we need to do, because we've stored them, we need to add these to our hacked hook function, and this is where we're going to actually hook the syscall. So we're going to overwrite the syscall table now. So let's do that. So we're on the hook function. I've just noticed as well, I forgot to put these on the end of the kill, so just do that and save. So now we're on the hook function basically. So we're going to do a comment, and we're going to do kill. So this is for the kill syscall, and to hook it we're going to do underscore sys underscore call underscore table. Then we're going to index it to underscore nr underscore kill. So just like we indexed it before, except we're not saving it to a function pointer. We are indexing the syscall table to the syscall, and we're saying that that equals, and then we're going to do ampersand and then hack underscore kill. So the ampersand is going to get the address of this hack underscore kill function. So that's basically how we are hooking it, because the syscall table is holding unsigned long addresses to the syscall functions. So we are giving it the address now of our hacked kill syscall function by using the ampersand, but we also need to typecast it to unsigned long because the syscall holds unsigned long values. So we're going to do unsigned long. So that's cool. We've now just overwritten the syscall table for the kill syscall to hold our unsigned long hack kill address. So that's good. So we've just hooked a syscall table, and because obviously no matter which version, whether it's PT Regis syscall stub or the other one, they both will have hack underscore kill, hack underscore kill. So we only have to do this hooking once. It doesn't matter which version we're using, it's still just hack underscore kill. So that's cool as well. And then we're just going to return 0. So we've stored the original syscall for kill. We've got a function that hooks the syscall table at the kill syscall and puts in our address for the hacked kill syscall function. And then on our hacked kill functions, we look out for certain signal values, and then if we find them, we print and then we return 0. And we also print that it went through our hacked kill syscall. And if we don't find it, we just return orig underscore kill, and then yeah, it does the original syscall that it would anyway. So that's cool. So now what we need to do is we need to go all the way down to the Init Mod. So here we go, we've got the syscall table. Just go into the syscall table function to get the syscall. Now if it's equal to null, and if not syscall table, then we print an error, we return the error, and that's it. If we get past that, we can then do if, and then store is equal to err, so error. Then we will do print k kern underscore err error store error /n, of course, /n. Let's use kern info actually, because I'm not sure kern error prints on the dmessage executable, so we'll just use kern info anyway. So now that we've stored the original syscalls, so we've got the syscall table, we are then storing the syscalls that we want to store from our store function. So we're only doing the kill syscall for now, and we've only obviously got a hacked kill syscall to hook, but you can obviously add more if you wanted. So we store it, and then we need to unprotect the memory. So unprotect underscore memory, and once the memory is unprotected and the write protection for the CR0 register is flipped, we can then hook it. So we can do if, and then hook is equal to err, and then we can do print k kern underscore info, and then error hook error /n. And then once we've hooked it, we need to protect the memory again, so there's no overwriting of those tables by accident by other bits of programs or whatnot. And then we just return 0. So that's cool. Let's just go through the code and make sure there's no errors or anything. Make sure it's all good. Yeah, I think it looks all good. We'll find out anyway soon enough. So we've done the init mod function. Now for the exit. So for the exit, we've also got a ERR is equal to 1. So when we exit the Linux kernel module, we need to obviously clean up. We need to clean up the syscalls. So we're going to have to unprotect underscore memory, and then we're going to need a cleanup function. This function is going to obviously overwrite the syscall table again with the original syscalls. So we're going to need to create that function. So we'll go back to the top, and we got store, we got hook, and let's create a static and then clean up. So we'll do int and then clean up and then void, and we'll create that function. So in the cleanup, all we need to do for the cleanup is we could just do comment kill. Now I would use a comment kill, and then for every other syscall use a comment as well. But we can do underscore underscore sys underscore call underscore table. We're going to index it, so underscore underscore nr name number reference, and then underscore, and then the syscall name, so kill. And then we're going to do equal, and then all we need to do is do orig underscore kill. So the syscall table is going to get indexed to where the kill syscall is, and at the moment it will be holding the address of the hacked syscall function, but we don't want it to hold the hacked syscall function. We want it to have the original syscall function, and what we're going to do is we're going to typecast it to unsigned long, because the syscall table takes and holds an unsigned long value. So we've got original underscore kill here, and yeah, nice and easy. And then we're just going to do return 0. And if you remember, the orig underscore kill is holding the original syscall address for the kill syscall. As we can see here, orig underscore kill equals, and then it's the syscall table being indexed to nr underscore kill, and then obviously we're just typecasting it to whichever type depending on the version, but it's still the address. And then obviously we're just getting that address, the original address for the syscall kill, and then just typecasting it to unsigned long, which is what this syscall table takes. So that's cool. So now we should be able to put cleanup into our exit module, into our exit function, and then we can test it out and see if everything is working. So we can do if, and then cleanup is equal to err print k kern underscore info error clean up error /n, and then we need to obviously protect the memory afterwards, like so. So yeah, it's quite a bit of code there. It could be a lot more obviously as well. So let's load up the VPS, and hopefully there's no errors and we can see it working. Okay, so let's go to the VPS. I'm going to put w3.c into there. I'm already logged on the VPS. So we're going to use the make file like we did in part 1. So I'm going to do make, and we got some errors. Okay, it happens sometimes. So I've already looked over the code, and I can see that I'm missing obviously the colon there. So I'm missing the colon, and we've got to include one more thing as well. We've got to do include, and then linux/dirent.h. Now this dirent is used for the it contains the struct, basically the pt_regis struct, I believe. Contains dirent structs, etc. It's also used for the directory entries syscall as well, stuff like that. So yeah, we'll save that, and now we will move the file over, Where is it? So we'll move this file over, and then we'll clear the screen, we'll do make again, and hopefully we shouldn't get any errors. Nice. So we can do clear, we can do lsmod, and we can see there's no W3 in here, but I have noticed that they've added some extra modules into my VPS, which is a little strange, but anyway. We could do demessage, so we'll clear this, so it's clear. Cool. So now we're going to insert a module, w3.ko. Now ko is what you insert as the module, but ko does stand for kernel object, just so you know. But yeah, let's insert w3.ko, lsmod, zoom in a bit so maybe you can see a bit better. We've got module, w3 is in. Let's do demessage. We've got rootkit init, and then we've got orig_kill table entry successfully stored. So we've stored original kill. We've unprotected the memory, and then we've protected the memory. So I'm pretty sure we've hooked the syscall table, but we didn't print when we actually hooked. If we have a look at the code, we've got hook here, if hook. So yeah, we haven't got a message to say that we've hooked the syscall table, which we could have done. We could have just printed here, print, and then kern_info, and then hooked function, something like that, just so you know. So we'll save that for next time maybe, but let's do demessage again. Okay, yeah, as we can see, we've got hacked kill syscall, so it's obviously the syscall kill is being used by other programs in the system, and it's going through our hacked kill syscall. It's obviously not the same number as the signals that we gave. If we look up here, it's obviously not the same signal number as 6463, because it would have said. So it's literally just printing hacked kill syscall, and then it's just giving it the original syscall to use, and no one's any the wiser. So that's cool. So now if we want to use our hacked syscall, we can use the kill executable, which is just a signal exe basically, and 9 would kill the process. But if we do -64, that's our signal number that we have got in the hooked syscall. So we do 64, any process ID. It's not going to actually do anything to a process because we return and we don't actually give it the original syscall kill to do anything. So if we do demessage, we can see we've got signal 64 is equal to sig super, and then become root. So you could you give it the signal 64, and then it runs a special function or does something special on the system. It's totally up to you. Let's do kill and then signal 63 and see. This might take a little bit of time to get through, and as we can see, we've got signal 63 is equal to sig invis 63, and this will hide itself, malware, etc. And obviously you can write the function for that. You can make it do anything you want basically. So yeah, pretty cool. We've hooked the syscalls, we've stored them, we've created some hacked syscalls to use, and so on. So yeah, cool. Let's remove it now by doing rm mod and then w3.ko, and we'll do lsmod. There's no w3 Linux kernel module. If we go to demessage, clear that, demessage, we can see that we've got rootkit exit, and then it unprotected the memory and then protected the memory. So yeah, that's nice. We've basically just done a little simple rootkit. We could have added in when it hooked and stored the syscalls and stuff like that, but obviously I did forget. But anyway, we can see that it's working because obviously it's printing when it's going through the hacked kill syscall. So whenever any program on the system is using the kill syscall, it's going through ours first, and when we use it with a certain signal number, it prints that and then just returns. So that's cool. So yeah, this is part 2. I'm going to say this is the last part of the rootkit tutorial. Part 1 and 2, they're quite long. Hopefully it gives you enough information to look into it more yourself and gives you a start on making Linux rootkits. So good job, hope you enjoyed it. Leave a like, comment and share, and I'll see you in the next video. Goodbye.
Hecha culo, hecho y actitud. Hoy te voy a buscar, ponte la mini, que hoy te lo meto en el Lamborghini. Trépate encima de mí, y ni yo la quiero como tú. Teta hecha culo, hecho y actitud. Hoy te voy a buscar, ponte la mini, que hoy te lo meto en el Lamborghini. Y ni yo la quiero como tú. Teta hecha culo, hecho y actitud. Hoy te voy a buscar, ponte la mini, que hoy te lo meto en el Lamborghini. Trépate encima de mí, baby, yo la quiero como tú. Teta hecha, culo hecho y actitud. Hoy te voy a buscar, ponte la mini, que hoy te lo meto en el Lamborghini.